Maunakea Speaker Series is a partnership between Hilo Astronomy Center, the Hilo Physics and Astronomy Department, and the Office of Maunakea Management. And really our purpose is to share some of the scholarship that's going on Maunakea and Hawaiʻi Island more generally. I want to introduce Dr. Don Thomas. He is the director for the Center of Study of Active Volcanoes here at Hilo. He got his doctoral degree from University of Hawaii at Manoa back in the 1970s, looking at volcanology. He has been working in recent years looking at groundwater, high elevation groundwater in the sense of groundwater in the saddle region. We've talked to him about stuff further up in terms of higher up on Mauna Kea, but tonight's topic is I think a general picture of the groundwater understanding on the island of Hawaii, and then more broad or more specifically some of the current research on Mauna Kea and what he's finding. And with that, I want to say thank you very much, Don. Are you good? Yep.
Very good. Thank you. Thank you, Fritz. Appreciate the opportunity. I thank all of you for coming out. I hope to make it worth your while. So what I'm going to do is talk very briefly about research that I've been working on, actually going on 2.5 decades now. Some of these projects I could probably talk an hour on individually, but what I'm going to try to do is draw a picture of the groundwater and evolving understanding of groundwater here on the Big Island, and also related to some of the things that we're seeing on the other islands as well. So let's begin. So we've had some models of Hawaii groundwater that I suspect that many of you are familiar with. They're relatively simple. I have to confess, I think in cartoons, so I'll be showing a lot of cartoons here, which my term for very simple conceptual models of how groundwater moves in Hawaii. And this is really one that you see very, very frequently. Okay, this is intended to depict the island. We have at the center of the island, we have a dike complex. These dike complexes are associated with drift zones or with the caldera of the volcano. And then the extruded basalts that are very permeable. And so all the rainfall that enters this system passes down and discharges into the ocean. And we've seen really remarkably little change in this conceptual model for our groundwater for a very long time. This is an image taken from a report that was published in 1935. And you can see very little difference between the previous model and the current one. And generally what we have assumed always is we have rainfall entering the ground, very rapid infiltration down to the basal groundwater system. The rule of thumb that we've always heard is that the groundwater, this basal groundwater lens, the thickness increases, or the elevation increases about 1 foot per mile as we go inland. And so we have a very thin basal groundwater system here that moves rapidly out towards the shoreline, and then rainfall up here in the elevated areas where we have dike complexes infiltrates into the dikes, and that very slowly discharges into that basal groundwater system. When we have erosion going on, you have very much the same thing, although in this case the dikes are forming springs where they've been exposed. But this water table always is assumed to be just a single body of groundwater. For those unfamiliar with hydrology, I frequently encounter sort of the idea of a big pool of water. Well, it's not really a pool of water, it's just that the rocks here are saturated with fresh water. All of the clinker layers, the fractures are saturated with fresh water. And then below that is a zone of mixing with salt water. But again, the general idea is that once you go through that zone of fresh water and get into salt water, all you're going to see, as deep as you care to drill, is going to be salt water. For the first time, in recent times anyway, we've gotten an indication that maybe this model is not quite complete, was the Hawaiʻi Scientific Drilling Project. That's a project that began actually in about 1986. We drilled a relatively shallow borehole and then a deep borehole. Let me talk briefly about the purpose of that project was to develop a better understanding of the origins of Hawaiian volcanoes. Now, those of you unfamiliar with Hawaiian geology, we used to call it the hotspot, the Hawaiian hotspot. We now call it the mantle plume. We have this planetary feature that extends down, we believe, to near the foremantle boundary. This thermal plume rises below Hawaii, and as it approaches the base of the crust, a portion of it melts. And as the Pacific plate moves to the northwest across the top of that mantle plume, magma accumulates under the plate, migrates through the plate, and forms Hawaii. And in fact, has formed all of the islands as the plate has moved off to the northwest. And so the islands are formed sequentially, and the volcanoes on the island are formed sequentially. Turns out this has some significant impacts on hydrology as well. So the Hawaiʻi Scientific Drilling Project was unique in a number of different ways. It was continuously cored. Typically, we have about 4,500 holes for groundwater that have been drilled in Hawaii. Virtually every one of them has been with rotary drilling. You grind up the rock, flush it away. You're not interested in the geology at all. You just want to groundwater. What we were doing instead was we were actually collecting samples of every single lava flow as we drove through it. So we have a continuous geologic record. So not only do we know where the water is, we know why it's there. And that's an important feature that we haven't really recognized before. The drilling was targeting an older volcano. Again, as I said, older volcanoes underlie younger volcanoes. Here in Hilo, we're on Maunakea lavas. The lavas, you go out and take a sample of that rock and analyze it. This is Maunakea. Turns out Maunakea is under Maunakea there. Maunakea is encroaching on Maunakea. And so we were drilling through Maunakea actually to get access to Maunakea. And this is a depiction of the island going down to the ocean floor. And actually, this is part of the Maunakea plank that has now subsided. One of the things that we found in this project was that Maunakea has actually subsided by more than a kilometer away, by 3,000, actually 600 feet, since the first subaerial lava flow was deposited at the location of our drill site, which is out here right next to the airport. This line marks the intersection of the encroaching Maunakea onto Maunakea. It was also one of the deepest holes that's ever been drilled into an ocean island. We drilled 11,541 feet. So we have a continuous geologic record going back, and that goes back about 700,000 years. And when we started the project, the groundwater, the whole study of groundwater was figured, well, go look at the salt water and see what you can figure out. It was expected to be totally boring. We didn't have any idea that, again, based on the existing model for groundwater, that there would be anything really interesting going on. As drilling progressed, sorry, I'm going to have to show you pictures of rocks. This is what the Hawaiʻi looks like. This is the aerial Hawaiʻi lava flow. This is we have the clinker layer here. This is the core, and then the underlying clinker layer. And actually, in hydrology, these areas are very important to us because those clinker layers are where most of the water flows within the island. But as we drilled, we passed through a freshwater layer, extended down about 200 feet. We went into salt water, always consistent with the original model. But as we got down to the bottom of the Maunakea interval, we began to see a significant number of ash layers. These ash layers look like this. They're much denser in terms of the ability to flow water than are the Hawaiʻi models. And at this intersection, this was the last Maunakea flow. We have a thick section of ash here. big section of soil here on top of Maunakea. And as we went through that section, we encountered a second layer of fresh water. And its depth was about 1,100 feet. The aquifer was about 400 feet thick, so it wasn't just trapped fresh water down there. It wasn't a small deposit. It was actually a river of fresh water, about 400 feet thick. And once we drilled into it, it started producing water about 2,100 gallons a minute. The point of reference at the time, that was about that's 3 million gallons a day. That's about as much water as the Hilo water system provides to the residents of Hilo. So a very substantial flow of water coming out of the well, completely spontaneous. The isotopic composition of the water, the isotopes are a tracer I'm going to talk about here in a minute. But the isotopic composition of the artesian water coming up indicated that it was from rainfall that had fallen at an elevation of about 7,000 feet on Maunakea. Again, our typical model of groundwater had been that, okay, you have local rainfall, it infiltrates down to the water table and flows out to the ocean. Sort of that high elevation water, kind of, we don't even think about. You have a question?
Yeah, when you bore down 11,000, where is sea level?
Okay, good question. Sea level, we actually started at about 25 feet above sea level, so we were right on the shoreline. We started actually as close to the shoreline as we could. So we take another quick digression. Okay, for those not familiar with isotopes, many of our elements have multiple isotopes. An isotope basically is say, oxygen. It has all of the chemical characteristics of oxygen, but it will have a different mass. So you have the same number of protons and electrons, but you'll have a different number of neutrons. And so the atomic weight's different. The principal isotopes we look at for water are oxygen 18 and oxygen 16, and deuterium, which is a proton and neutron, and hydrogen, which is a single proton. And I hope I can make this work. The ocean is defined, the term we use is delta O18. That means how much does the oxygen 18 content of that water differ from a reference water. And that reference water is actually ocean water. Ocean water is defined as 0 delta O18. It turns out that during the evaporative process, O18 does not evaporate as efficiently as does oxygen 16. And so in marine vapor and marine clouds, the oxygen, the delta O18 value is minus 13, meaning that it has significantly less O18 than the ocean water from which it evaporated. Same process happens in reverse though. As that water condenses at rainfall, it becomes enriched in oxygen 18. And so the first water that hits the ground here on the shoreline will have an oxygen isotope ratio of -3. But as the clouds move further and further upslope, the rainfall becomes lighter and lighter. And suddenly we have a tracer that we can use to look at groundwater and determine at what elevation, what average elevation that rainfall fell. And so we can trace that water back to its source elevation. Turned out the water from the HSDP, this was some work that was done by Martha Scholl of the USGS. She put out a whole sequence of buckets from shoreline all the way up to the summit of the wall. And these are the data values she got. This value here is the oxygen 18. This is the elevation in meters. So near the shoreline, we're seeing -3 as my previous picture showed. And right here was where the HSDP, where the artesian water was, at an elevation of about 2,000 meters or about 7,000 feet elevation along the bay. And it turned out the age of that water, we were able to determine its age using carbon-14, approximately 2,000 years old. So it had taken about 2,000 years from the time that water actually infiltrated into the ground at 7,000 foot elevation. Okay. And when that happens, that infiltration process, the water absorbs what's called root-respired carbon dioxide. Carbon dioxide generated by the plants at 0 age is absorbed by that water, and that carbon dioxide stays with the water through the entire cycle. So that allows us then to tell how long that water is traveled underground to get it down to the point where we're standing. So based on the thickness, age, and the distance traveled, we can estimate the discharge through this, what I'm calling an underflow system, maybe a couple 100 million gallons a day. We don't yet know really how wide this system is, but given 400 feet thick and moving at the rate that we can calculate from that age, this is a rough estimate of how much water is discharging at a depth of about 1,000 feet below sea level. So this is my cartoon for the groundwater system here on the Hilo side. We drilled through the Maunakea basal groundwater system where it's going into Hilo Bay, and some of it appears to be discharging into the ocean actually below the bay sediments, salt water, and then these barrier layers of ash that have trapped Maunakea water, forced it below sea level, and is discharging into deep submarine springs. Just by an odd piece of good luck, back in the 1970s, a graduate student was doing a geological survey down the submerged slope of Maunakea, and he actually did see evidence of freshwater discharge. So we're able to complete that entire cycle. So this is what we found in the Hawaiʻi Scientific Drilling Project. Now we continued drilling, and as we got to greater and greater depths, again, the Siberian lavas converted to submarine material. This is the stuff that's being generated as the lava flow goes into the ocean. But as that material gets buried deeper and deeper, it becomes compacted and actually becomes very impermeable. It then becomes a barrier to water flow. And eventually we encountered at 6,500 feet these lavas, which were fractured, they're pillow lavas. These are lavas that have been erupted underwater. They're fractured and they're permeable. The interesting aspect of those pillow lavas was that they were saturated with water. They were at high artesian pressure. This is a photo taken on our rig floor as they opened up the drill pipe to add another piece of drill string. At one time, we were seeing pressures of about 165 pounds per square inch out of this the deep part of that borehole. And that water was fresh. So completely unexpected. No one, when we started the project, had any idea that we would ever see fresh water through this kind of depths. So this is my cartoon for the deeper part of that hole. We had the Siberian lavas, the pyroclastites, that's a fragmental material that was very mushy. And it's kind of a scary thought that all of this nice solid Siberian lava flow is kind of sitting on top of a pile of mush. But that mush eventually gets consolidated, and then below that we have these pillow salts that are saturated with fresh water. Now the problem there is, based on the accepted model for groundwater here in Hawaii, we should have a very thin basal lens that increases the elevation as we go in by only 1 foot per mile. So in the center of Maunakea, say 30 miles from the coast, we should only have 30 feet of fresh water above sea level. The problem is, in order to get fresh water down to 10,000 feet below sea level, and we did see it as deep as 10,000, we have to have high level water within Maunakea. We have to displace that seawater. We have to have pressure to displace that seawater and get that fresh water down to those depths. So we wanted to test that idea. So we conducted a series of surveys using geophysical methods across the pool of sand. Again, I'm going to get down in the weeds here a little bit. We use the magnetotelluric method. And what this method does is it measures the electrical conductivity of the rocks below a station that we set up on the surface. We can actually use this method to see the depths of 20, 30, 40, 50, even 100 kilometers under the right conditions. We were using a very simple principle though. Wet rocks are electrically more conductive than dry rocks. And this is an image that just sort of shows the range of electrical resistivities. The term that we use, ohm meters, But basically, it's a relative resistivity. The dry basalts fall in the range of 10 to 20 to 30,000 millimeters. That's the resistivity of dry rock, dry basalt, where the wet basalt falls in the 100 to 1,000 millimeters. It's a passive, non-invasive method, meaning that all we have to do basically is set these instruments out on the ground surface. We don't have to drill a hole. We don't have to really disturb the ground surface. And we're using naturally occurring radio waves that induce currents in the subsurface. And one of the principles of this whole method is that low frequency signals can penetrate much more deeply into the ground than high frequency. So what we're actually using to look at very shallow resistivity, we'll use lightning, the electrical impulses generated by lightning. But for deeper, we use signals that are coming from the ionosphere or even signals coming from the magnetosphere. Okay, we're all familiar with radio waves of, say, 10,000 cycles per second. The signals we're using are in the 10,000 seconds per cycle range. So we're using very, very low frequencies to be able to see to these depths. So we began the survey right near the Saddle Road well. It's an elevation of about 2,000 meters, and installed stations across the saddle almost over to the Maunakea Highway. And what we found, this is a what we call a pseudo cross-section along that transect across the saddle. It's as though we have cut the saddle in half, and we're looking at the electrical resistivity where the warm colors in this case are extremely resistive. The cooler greens and blues are much, much less resistive. So very resistive rocks here are in 20 to 30,000 millimeters. But the wet rocks, again, we use a known water table right here at the Saddle Road well. We see that Maunakea basalt saturated with fresh water have a resistivity between 600 and 1,000 millimeters. So once we got this data, it was a very simple process of simply looking at these lines. This is the 1,000 millimeter, this is the 600 millimeter. And so basically somewhere within this region, we have our best chance of finding water. One of my cohorts who's spent a career working on this has said that there's a lot of uncertainty in the method. That you can have many things that will generate this low resistivity. But if you see high resistivity, that tells you there's no chance whatever for finding water. And so what we're doing is we're identifying those areas that we're not the least bit interested in, trying to increase our odds that where we have these low resistivities, we would have the best chance of seeing high elevation water. In this case, the elevation of the presumed water table was about 4,500 feet above sea level. So that happened to be located right here, right next to the Maunakea training area. And so we drilled a borehole there down to a depth of about 5,780 feet. And as expected, again, this is one of the lowest rainfall areas on the island. Shallow interval was dry, bone dry. But at only 700 feet, we encountered our first saturated water level. And that really had us scratching our heads because that was much shallower. We started drilling at 6,300 feet above sea level. So this was actually much shallower than we were expecting to find any water at all. And that saturated layer extended to about 1,200 feet depth, or an elevation of about 5,100 feet. Top casing was about 6,375. Below that zone, though, we started seeing a drop in the water level. And when we looked at the core, we found that at 1,180 feet, we have this layer here. This brick texture tells us that that section of rock is very clay rich. It turns out that 1 foot thick section here was actually the perching formation, the layer on which that water was standing. Once we drilled through it, we saw that water level immediately begin to drop. But the We continued drilling and got down to a depth of about 1,800 feet, or about 4,500 feet above sea level. And from that depth to the total depth drilled, we had water at 1,800 foot depth for about 4,500 feet above sea level. We believe that that deeper zone is the regional aquifer for the saddle region. Outlined this in blue. The resistivity is basically within this region is consistent with there being freshwater saturated rocks, certainly up at these elevations. We believe this little knob here in the resistivity is probably our perched layer. So that perched aquifer is a good deal smaller, but the deeper zone is pretty big. Based on the nature of the core, and this is again one of the advantages of doing core drilling, is we can actually look at the rock and come to a better understanding of why that water is there. We believe that this is a dike pounded system. Partly we have this material here is dike material. We can recognize dike material as magma that's been injected underground on high pressure. It has very few vesicles in it, although it looks highly fractured here. That fracturing is actually post-drilling. Turns out this whole region is under tremendous lateral stress. We discovered the rocks actually were fracturing as we were drilling. And an analysis of the gravity field on the island. We have over the past 20 or 30 years done a number of gravity surveys. Basically, we have a device called Remember. We go out and measure the force of gravity around the island. And what that tells us is actually the density of rock below that station. And so these folks developed a model that would incorporate the entire island. So the dark areas here are the highest density. And these, of course, are the cores of Kohala, Maunakea, and Maunakea. Interestingly, Hualalai doesn't seem to have that very dense core, and Kilauea has not yet developed. But the interesting aspect is this sort of tan area that surrounds all of the central volcanoes on the island. Our well is located in here. That high density is in part attributed to the presence of dikes. These dikes are more dense than the erupting rocks. Also turned out that as we drilled, we encountered a temperature gradient of about 165 degrees Celsius per kilometer of depth. This is about 10 times the normal temperature gradient that we would find on the island away from any volcanic intrusive bodies. And so very clearly there are intrusive bodies within this region at this time. So we continued the project. We wanted to test the extent of the regional aquifer. And so we drilled a second borehole further to the west, located over here. And again, we can see this resistivity feature extending out here. And it was located here, right in the junction between the old saddle river and the new saddle river. The findings there were actually quite, I would say, equally surprising as the ones that we got in the first borehole. Instead of finding just a single perched aquifer within a larger regional aquifer, instead we found a sequence of confined aquifers. These are aquifers that have sort of a capping formation and a supportive formation. I'll show you the cartoon here in a minute, but essentially this is a record of our drilling. The red line is the depth of the borehole. These blue lines are the elevation of the water inside the borehole. And so as we drilled, we got down here to 1,000 feet. We saw no evidence of water. We got down to about 1,050 feet, and over about a 20-foot cycle, we ended up with 600 feet of water coming up the whole edge. We continued drilling, and we drilled through the supporting formation, or the perching formation. The water went away again. Continued drilling, got down here about 1,800 feet. We saw the same thing, and basically the rest of the hole, we were seeing water rising and falling. What we looked at, the core and the confining layers are mostly clay and ash elements. Again, these are this brick-like texture is telling us that we've got a clay-rich layer. This is a tephra ash layer. We're probably good 15 kilometers from where the summit caldera of Mauna Kea was when this was erupted. So this was probably a pretty significant eruption. This one was even more striking. This confining layer starts here, extends through here, all the way down to here. So we have about a 15-foot thick layer. This is a close-up of some of this rock, and what you can see are these very angular fragments that are mixed in with welded ash. This is an explosion deposit, and it probably was a very sizable explosion because that was the confining layer for this particular zone here. We had water rising 3,500 feet above the point of entry as we drilled into that aquifer. So this aquifer has to extend at least to an elevation 3,500 feet above where we were actually drilling. So these varying layers are a history of the eruptive activity of Mauna Kea. And in fact, they could possibly be layers that have been laid down by extremely explosive activity from Mauna Kea and Mauna Loa. The chemical analysis of some of the layers in these cores actually do look more like Mauna Loa than they do like Mauna Kea. So that would suggest that these were some fairly extraordinarily large eruptive events to lay down these confined layers. And the varying hydraulic characteristics of these different layers clearly have a much greater influence over how groundwater moves and how it's stored within the island. So with the confirmation of these high elevation zones, we conducted some additional geophysical surveys, and actually we pretty well encircled Mauna Kea now. But this zone here, I'm going to show something. This was a sequence of surveys that we did across the Department of Hawaiian Homelands. They own property extending from the Saddle Road region all the way over here. And we, of course, were in communication with them when we found high elevation in the Saddle. And one of the things they told me was that one of their biggest challenges to making that land available is the absence of a reliable water source. And so this survey from here to here, move that out of the way a little bit, is extending from here all the way over to here. And as I was saying before, the range of resistivities of water-saturated rock on a Kea basalt is somewhere between 600 and 1,100 meters in the sort of greenish blue color. And we can see, actually, we have resistivities that are consistent with fresh water over here on the eastern section of the survey, over here in the middle, and further over on the north end of that survey. So this is, again, very suggestive that we have these confining layers, we have these saturated zones that are substantially higher than our old model indicated. Now these red colors here actually are very low resistivities, and we believe they probably represent leakage of thermal fluids out of the core of Mauna Kea. So there may also be geothermal resources under this Department of Hawaiian property as well. So the dike impounded systems were already part of our original model, but these, what I'm calling sub-horizontal confining layers, are generally discounted as having a significant effect on groundwater storage and flow in Hawaii. Simple conceptual model for what we're seeing. You have a cartoon here. Different things that could be happening. These may be just sort of dead-end systems here that are simply storing water in a pocket that will accumulate and gradually leak away with seasonal changes in rainfall. rainfall. Perhaps they're serving as conduits to carry high elevation water down into the basal groundwater system and continue to feed that system. However, it's also possible that we have water that's confined, that's completely bypassing the basal groundwater system and extending into the saltwater saturated rocks. This is kind of a cartoon of our basal groundwater system, freshwater, saltwater here, or possibly bypassing that system entirely and discharging out into the ocean, similar to what we found here in Hilo in our Hawaiʻi Island project. But do we have evidence, other evidence that these systems exist? Turns out that we do. In terms of that long distance transport, a graduate student recently did a study. He was looking at the groundwater here in Hilo Bay. Turned out the isotopic composition of that freshwater, of the freshwater fraction of that water, looked like rainfall that had fallen at about 10,000 foot elevation on Maunakea. The interesting and surprising thing was that it hadn't mixed with any of the other rainfall between the point that it hit the ground and the time it got to the shoreline. So that suggests that there may be discharge of this confined aquifer down here at the shoreline. I think more significantly, though, over in the Keimo aquifer, this was something that you may have seen in the newspaper. There was a couple of years ago. There's a high-level aquifer here above Hilo. And when we look at the isotopic composition of that water, it turns out it doesn't look at all like local rainfall. It looks like actually rainfall that has either come from Mauna Loa or Maunakea. Because in order to get the isotopic composition of this water, that rainfall has to hit the ground higher than Mauna Loa. So what we're seeing is actually water moving from Mauna Loa through the line on its way to the shoreline. A couple of interesting wells have been drilled. This first well was the Kamakana well. It was not drilled in this high-level aquifer. It was drilled down slope. This is an image taken of a salinity profile in the well. Essentially, these values here are in terms of the salinity of the water. Seawater has a salinity of about 35. And measurement when the hole was about 950 feet deep, this green line shows a very thin basal lens, and this is a big problem in the Keimo aquifer. All of the nearshore aquifers are very thin and very fragile. When you start pumping off, they almost immediately go stable. So, as expected, as you get any depth at all, it begins to go saline very quickly and quickly becomes seawater, entirely seawater at depth. However, the driller continued to drill down to a depth of about 1,050 to 1,100 feet. And this is a second profile, salinity profile, taken after he got to that depth. What this shows is he had fresh water again below 1,050 feet below sea level. This water is flowing into the well and then mixing with salt water, rising up and then discharging into the transition zone at around 200 feet. So what we're seeing here is a very close analog to what we found in Hilo. Fresh basal groundwater, salt water, confining layer, and more fresh water below. More recently, the state drilled a deep monitoring well, the Geophysical well, and they also drilled to about 1,000 feet below sea level. And when they reached that level, they set casing, and that well was producing fresh water. They actually did a pump test and pumped about 800 gallons a minute, a minimum drawdown, and a salinity of about 5 parts per million. Extremely good quality water. The interesting aspect of both of these wells, again, going back to the isotopes of that deep water looks exactly like the water in that high-level aquifer. So we see more generally a dividing line here. This wells drilled above this dividing line have lighter isotopes very good quality, high elevation. Below this, we have local rainfall only. But if we drill deep enough, we get into fresh water that is flowing below that aquifer. This is another of my cartoons. What we're seeing is we've got these confining layers buried within the flank of the wall line. And we see a very thin basal lens near the shoreline. It jumps up from about 5 feet above sea level to about 400 feet above sea level. Drill into it, we can drill into that thin basal lens, we drill through mixed water and back into fresh water below. Let's see. Oh. Question, do we have evidence that these exist in other locations? I was quite excited because I thought this was a brand new discovery. The layered groundwater system up in the saddle. But then I remembered some work done by Gordon McDonald and Harold Stearns on Maui. And they had drilled a sequence of boreholes on the east flank of Hawaiʻi Island. And this is what they found. In a similar fashion to what I showed, this is where the depth of the hole, and this is the water level. As you can see, as they progress deeper and deeper, the water level rose substantially above. So apparently the same type of system exists on Hawaiʻi Island, where we've taken control of the look, as well as on Oahu. There are a number of deep monitoring wells that have been drilled. This is kind of what the salinity curve is supposed to look like in these wells. And what we find instead is they do go saline, but we have, you can see the change in the salinity as fresh water has entered the well below where we would expect salt water to be. So based on this data, we really have to say it's time to revise this groundwater model. We're not seeing just a single uniform basal groundwater system. We're actually seeing a sequence of buried channels within each volcanic edifice that can accumulate water and transport it down to either the subaerial shoreline or actually discharge it well below sea level. So why should we care? Well, the good news is there appears to be a lot more water stored, certainly within the Big Island than we ever realized. Yet, before we started the project up in the south, we were expecting to see a groundwater elevation of maybe 500 feet above sea level, if we were lucky. Instead, we're seeing a large regional aquifer more than 4,500 feet above sea level. So it's telling us that we have a substantial quantity of groundwater stored. Bad news, though, we regulate water based on simply the geographic location of the well. We have, again, this very simplistic model where we have rainfall coming down, hitting the mountains, migrating out to the shoreline. The concept that we use to regulate groundwater in Hawaii is what's called sustainable yield. That sustainable yield is how much water can you withdraw from an aquifer without damaging that aquifer, by damaging, I'm saying, by drawing salt water up into the aquifer or depleting the aquifer to the point where we don't have any flow out into the shoreline. And this is a map that the Commission on Water Resources Management uses to regulate groundwater. Here on the Hilo side, we don't have an awful lot to worry about. What's the number? We have a sustainable yield here of 341 billion gallons per day. We got lots of water here in Hilo. Hawaii, 437 million gallons per day. Over here, though, in the Hilo aquifer, we're looking at, I think that number is about 30. But each of those sustainable yield numbers assumes that all of the water, all the rainfall that falls in this region migrates out and passes through the nearshore basal aquifer and goes into the ocean. But in fact, the aquifers are three-dimensional in nature. When we have vertically stacked aquifers, if we're only developing that that very top aquifer, we run the risk of actually depleting it beyond its capacity, because we assume that all of that high elevation water is passing through that system. And in fact, we do risk overdrawing that while we ignore these deeper productive aquifers. It also has the potential to affect the nearshore ecosystem. One of the things that is a given that we all sort of that have looked at oceanographic chemistry, we know is that the surface of the ocean in the middle of the ocean is very nutrient depleted. And the ecosystems along our shorelines depend on the nutrients that fresh water carries out into the nearshore water. We could, in fact, develop these deeper aquifers and leave the shallow ones alone. And the deeper aquifers are actually discharging into already nutrient-rich water. So the loss of those nutrients going into the deeper offshore waters would have negligible effect on the ecosystems there. So bottom line is there may be better ways to access our water that will have less environmental impact and ensure that the resource is sustained in the long term. So our take-home message, simple models that we have of the island hydrology are useful in uncomplicated systems and situations in a nearshore environment, but those models really can't tell the full story of groundwater flow and storage within our islands. And any model that pretends to be realistic has to take into consideration these structures that impact groundwater flow. And with that, I'll be happy to answer questions. Thank you very much. Please don't be shy. I like questions. Yes, sir. Fluoride. Actually, excellent question. Fluoride in Hawaii's groundwaters are quite low. Actually, one of my cohorts here, Tristan Cumber and I did a study some years ago on test water. And what we found was that the emissions from Kilauea do contain fluoride. We didn't find any catchments that exceeded the World Health Organization limits on fluoride, but it's very clear that sort of with this ashy eruption, if you're on catchment, you want to think about testing your water for fluoride. But in terms of the fluoride in the groundwater, the levels are actually quite low. No, they don't. No, there's no additives. The only additives to your drinking water will be chlorine, just to control any biota to ensure that it's safe to drink. Yes, sir. Okay, two questions. One is nutrient-rich water going into the nearshore waters. What are they? The nearshore waters, the primary nutrients, sodium, potassium, calcium, silica, and silica is actually one of the most depleted of the elements in the ocean water, and is an essential compound for the microbiota in the ocean. Among the other nutrients, ammonia, there's trace amounts of ammonia in that water. Ammonia is also heavily depleted in the surface ocean water. And we do look at the water as the water ages. It does have slightly more silica, and some of the other nutrients, although they don't increase substantially. The ocean actually itself is layered, where much of the biologic activity occurs at the surface. It depletes these essential nutrients, and when they die, they actually carry those nutrients down to the deeper water. So the deeper water has a higher concentration of those nutrients below the surface.
Don, I'm going to pass around my
Okay.
Thomas, I have a question that
refers to the Hilo and the Hilo, and the controversy arising out of the treaty that and what its impact is on the coast environment. My understanding is the state drilled several wells there that supply their water supply along that coast. And looking at your presentation tonight, it looks like you find fresh water under 1,000 feet when you get down to that lower aquifer that we're talking about. Yeah. What is the state's well depth that they're bringing water out from? And are they the ones that are causing depletion in the aquifer right now? And should new wells be drilled that reach down to that deeper level?
Okay. Everybody, good question. And a couple of things let me correct. Actually, the only wells the state drills are monitoring wells. They don't drill production wells. The county of Hawaii has drilled a number of municipal wells, mostly up on that upper high level aquifer. And the controversy really was built around a model that was the conventional model, that high level water was actually recharging the coastal basal aquifer. And what our data found was that the isotopic composition of the high level water was markedly different from the composition of the water down near the shoreline, which invalidated that model. That high level aquifer, there may be some leakage into the near shore basal aquifer, but the majority of that water appears to be flowing literally below the basal aquifer along the shoreline. And this would be a case, in fact, where if they drilled into that deeper aquifer, preferentially over shallow wells into the shallow basal aquifer, they would actually help preserve that shallow aquifer while still being able to provide water for the community.
Thank you very much. Sure. You tell me where to go.
Okay.
Hi, Tyler from FAKO. FAKO community is currently going to have a biomass plant power production going online at the end of this year. And just community reports this last week, they've denoted that they are going to be pulling, they are seeking a number of wells, and they're getting these permits right now under approval. First of all, I'd like to know, there's a couple of questions I have for you, and then I'd like to the first is did they ever consult you with all the knowledge that you were doing about this particular power plant? Because they're supposedly going to pull 23 billion gallons a day at the site. Okay, so it goes right into them depleting the aquifer, potentially affecting the aquifer. It looks like they're going to go for that fresh water layout. And then what they're going to do is on their discharge water, they're going to push it down into the seawater. They're going to push chemicals and treat the excess water and force it back into the ocean. So there's a lot of controversy that people don't even know about that. First, is the consulting, has it occurred to you or come to you? Because the county's making the decision on it now. And they did not have an environmental impact report. They're basing off a whole so there's been no investigation, and your opinion is could this amount a huge draw? And is there another well that's going to draw this much water in a day for industry? So it's kind of a question that I'm actually not sure.
Yeah, I don't do consulting, so they have consulted me. In terms of sort of the impact, again, I don't know whether are they talking about fresh water or salt water. Brackish water. Okay, so.
And fresh and brackish.
Okay.
The brackish depletes the wood fresh.
Okay, well, again, the brackish water would typically underlie that fresh layer. And I don't see where that would necessarily have an adverse effect on the fresh aquifer. But if we go back a couple of slides and what is we're seeing, okay, within this region here, again, the way the state regulates, 147 billion gallons per day. Within this region, 150 billion gallons per day is what they consider to be the sustainable yield. So again, without a lot more details, I really can't offer an opinion one way or the other on exactly.
The stuff going back into the brackish water being cost effective.
Yeah, I don't know what the chemistry is. If they're using brackish water, I don't know what their additives are. Yeah, I'm very reluctant to give an opinion without all the facts.
Do you know of a 23 million gallon well?
I would suspect that Helco, they've got a well field here for the power plant in Hilo. And it could very well be that, given the size of that power plant, I assume that the power plant, the biomass plant is using that for cooling water. And given the size, I suspect that the Helco wells are going to be in that same region.
Who's paying for the exploration? Because you got a whole bunch of information there. And what I'm leading up to is, I heard you say that the temperature was rising. I know that you had a freshwater permit. Yes. You were really looking for heat. But what I'm getting at is geothermal heat on the unit. Could you talk about it a little bit?
Sure. Basically, the various projects, the first project that we did here at Hilo was National Science Foundation. Funded that. That was a research project. The project that I'm doing up in the Saddle is funded by a program that's called the Cooperative Ecosystem Study Unit. It's a federal program under the Army Corps of Engineers where we can, actually I say we, anybody can do sort of environmental type investigations to better understand sort of the ecosystem within that particular region. And so that was the agency that provided the funding for the drilling work that we did. And then the geophysical work that we did on the Department of Homeland, that was funded by State of Hawaiʻi, Department of Business Technology, tourism. And actually, I mean, a lot of the stuff we're doing kind of on a shoestring. I failed to mention another study that I'm really excited about. I'm working with the Department of Water Supply here on the island. They regularly sample for all of their active wells on a monthly basis. And so what they're doing is collecting a sample at the same time for me, and I can go up and what I'm doing is looking at the isotopic compositions of all of these production wells. And I'm hoping to get about at least a year's worth of data, or monthly data, to see how the isotopic compositions change over time. And again, try to get some gauge of how resilient these aquifers are to changes in rainfall. But in terms of the sort of findings of heat, these were completely unexpected. The Saddle was not a region we had ever looked at as having geothermal resource potential. But we had suspected that Maunakea would have some residual heat. We had anticipated that would be in rift zones and not sort of in the Saddle region. So this is kind of forcing us to rethink where prospective geothermal resources may exist on the island and on the other islands as well. So there's often many different findings from these projects. Here.
Talk about hot water, and you were working on Hilo, but I'd like to understand how the lava interacting with the groundwater producing the explosions, if that is what is producing the explosions.
Well, actually, that's another situation where new data is giving us some very new ideas. What we're seeing right now with Kilauea is to a degree a analog to the 1955 eruption, where a whole sequence of vents opened along the East Rift Zone and drew magma from the summit. But it's also a bit like the 1924 eruption, where the summit had a lava lake, it collapsed, basically drained down. And what followed then was a series of explosive events that sort of modern geologists had assumed were associated with groundwater. As the magma left, groundwater pouring into that still very hot conduit, generating a tremendous amount of steam pressure and generating those explosions. But with this current event, what I understand is that what they're seeing is much more magmatic gas, as though the rocks collapsing into the pit, where how the mountain used to be, is actually trapping the magmatic gases that are naturally coming out of the magma. And that's actually generating that force to blow that material out. But you know, the interaction of groundwater, this is a fairly common event in active volcanic systems, where groundwater infiltrates into magmatic conduits, and you end up with what are called phreatic eruptions. The interaction of groundwater, and they can be of varying sizes. Actually, during either the 55 or perhaps the 60 eruption, again, similar vents, fissures opened up down to Kapapa. But because the groundwater was so shallow, they had these very spectacular fountaining eruptions as magma was mixing with groundwater. And so you had sort of, in this case, a phreatomagmatic eruption. But again, it's just high heat, water, boom. Question here?
All such information in this presentation. I have a question on the middle aspects of the water deeper down. I'm more interested. But is the water deeper down, the lower levels? How cold are they?
How old are they?
No, cold.
Cold. Well, the temperatures sort of at the top of that water table started out, well, let me back up a little bit. In the first aquifer, the temperature of that water was only about 60 degrees Fahrenheit, which is sort of the average air temperature at that elevation. When we hit the deeper aquifer, temperature rose to about 80 degrees Fahrenheit. And as we drilled, we got down to about 3,500 feet, and that's when we started seeing this gradient temperature increasing. And we stopped drilling when the temperature got to about 212 degrees Fahrenheit. It was a water exploration well, not a geothermal exploration. Yes. But we got multiple questions.
To try and get an explanation on the Hilo aquifer a little more detail. You say you're kind of drilling higher level water from a higher elevation.
Yes.
Is it a might benefit if we drill a lower elevation?
Yes. Yes. The idea would be go down to a lower elevation, drill down into that underflow region where that high level fresh water clearly is flowing below the salt water, and drill into that and produce that water instead of water from the high elevation.
How high? And I would just think it's easier to pass water high and low.
Well, actually, the high elevation aquifer, they're drilling from an elevation of about 1,600 feet. They have to drill down to between 200 and 400 feet above sea level. So they actually have to lift that water by 1,200 feet or more to get it into their water system. And that's very expensive. And if you've been watching the newspapers, you're going to have a lot of trouble with it as well. If they go down to a lower elevation, most of that trip of the water coming up from 1,000 feet below sea level costs them nothing. It will rise spontaneously up to sea level. And so all they would have to do is lift from sea level up to the elevation of the well. So they can substantially reduce the cost of producing the water and sort of the difficulty for their pumps in terms of being able to maintain those pumps. Questions out here, please? Back, and then there was some more up here. Okay. You can stand or I can stand.
I'm interested in the water, the saddle area, Wakuloa. Has that been tested for contaminants in military training in 70 years? Is that information available to the public?
Yes, it has been tested. We've done a complete drinking water screen on that deeper water, and we found no man-made contaminants in the water at all. That shallow water has not been tested yet. That's a second phase of the project that we're pursuing right at the moment, and we will do a complete drinking water screen on that water as well.
What do you get access?
Once we're done with it, done the analysis, we'll publish that data. Let's see, we have some questions here.
So my question is about the isotope analysis method that you use, specifically on Maunakea. I was wondering, what is the highest elevation that you see
in the deeper aquifer up in the saddle, the elevation of rainfall there was about 10,000 feet. That was, again, the average elevation. And this is one of the interesting things in the work that we're doing with the county's Department of Water Supply. Their nearshore wells, we see no evidence of high elevation water in them. I mean, it's all rainfall from less than 7,000 feet. So, for what, at least tentatively, conceptual model is that what water infiltrates up in the summit region, maybe that water we're seeing 10,000 feet below sea level. We just simply don't see much evidence that it's making it down to the shore. So,
The two costs for private individuals to drill their own well without creating.
It is very expensive. There's quite a small number of well drillers here in the state, and sort of the number that I keep hearing in terms of the cost of drilling is $1,000 a foot. So these wells are pretty expensive. That's in part the reason, I guess, that most of the groundwater wells have been drilled for sort of municipal use rather than for individual homeowner use. And we're drilling through the salts, and the salts are notoriously difficult to drill. I think I guess there's a question here, a question back there.
Actually, I have two questions. When you drill along the on a road,
Well, we didn't drill along the Mono Road, we just did the surveys there. Not on Mono Road, no. All that we had done there was the physical surveys for non-invasive type work. And the non-invasive type work is a whole lot cheaper than drilling $1,000 a foot. And sort of the idea is that we can do the surface geophysics, minimal environmental impact, and then identify those locations that would have the greatest prospect of success. So essentially we save money and protect the environment.
are you a woman? See this at the ranch?
about a 23-mile market. She has springs. Springs,
Frank, yes.
so there's also springs on the base of the mountain.
Yes, and that was kind of what I was showing in my little cartoon, that, some of those things some of those perch aquifers may come out at the surface in spring.
When you get DGL, you get the report from Department of Homes. I'm asking that question because I'm working on homesteaders. And right now, we're working with the DGL to look at opportunities we have in Luna. So how do they know that there's access to water? Keep telling us no more of it.
Well, I presented a report to them, probably a year and a half ago, to the entire board. Sure. I'm happy to talk.
I was curious about what you guys might be learning about voids in the rock, and then my curiosity is, do these fill in over time, or is it just a new an A-stack when you drill that actually getting out?
I think it probably is something of a needle in a haystack. We actually, what we drilled now, 3, 4, 5, 6 kilometers, and I think we've only seen 1 or 2 locations where we saw anything that looked like a lawsuit. I mean, we know they're there in some of these locations, but they're certainly not common.
The Hilo well, which was drilled many years ago.
Yes.
Great. The Hilo well, which was drilled many years ago, great resource. Hilo are still messing around and not letting anybody use it?
So far, I don't know. I don't know what has happened. I guess we drilled 2 wells. One was a pilot well that was out by the agriculture center, and then the other one is next to the airport. And that one we have a cap on it, but nothing to my knowledge has happened with it. I know there were plans to do something with the land out there, but of course nothing has happened in 10 or more years since we finished our world. But let's see. Let's have a next question.
When you were talking about the KFO recharge rates, what I'd like to know, especially with currently a dry side recharge area, do you know what the sustainable recharge rate is? Doing a lower borehole, doing a lower thing, or the artesian well effect, because obviously that will run out as you start running down.
Well, let's see if I can get back to what we have is sort of these aquifers here may very well be serving to recharge the KMO and the Hilo Bay aquifers, and 35 million gallons today, 38 million gallons. Again, I believe, based on the isotopic composition of the water, that we are getting water from this region. And this is one of my complaints with this map, is that it was drawn almost arbitrarily, kind of along the surface expression of the different volcanoes. This one is a particularly sore spot because this was just simply the saddle road. There's no geologic reason for drawing a line like that. And again, I mean, we have situations like this where we have the Waimea aquifer, but clearly Waimea, this region of Maunakea is covered in Kohala volcanoes. And I expected if you were to go up sort of right near this boundary and drill, you would probably be drilling into a Kohala aquifer there. And very different available groundwater.
So really low.
Yeah, so on the leeward side, certainly I'm not advocating for squandering the resource.
Quick question about cold water. Where is the cold water from down in the cold pond, up along Cape Cod?
That probably is coming sort of from upslope here on Maunakea. And some work done by the U.S. Geological Survey. And they did a number of analyses of the water in here. And a lot of the age was in the range of decades, 10, 20, 30 years. So this surface water moving through the system is moving through quite fast.
Is it cold?
Essentially the elevation of the rainfall. As this rainfall is entering the ground at higher and higher elevations, I suspect again it's isolated from the lower elevation rainfall, which is warmer, and so it discharges as colder than for the average groundwater temperature.
So Don, Richard has the microphone, then one in the neck, and then I'm
Okay.
going to kill your computer.
All right. Okay.
John, I'm asking about hot water, and because of the threat to the PDB. Now, when you drill up the borehole, you said you're supposed to be doing something. Now, what I'm curious about is how fast was the temperature changing when you got to 12, and what temperature do you need to get your
Well, the rate of change, as I mentioned, there was about 165 degrees Celsius. So if we were to drill, say, another kilometer down, we would be at between 265 and 300 Celsius, which would be certainly an adequate temperature to generate power usage from. So perhaps another kilometer down, they could potentially find certainly temperatures that would be viable. But of course, temperatures by themselves don't necessarily be the resource. But certainly, there is some potential there. Okay, next question.
So did you say that there was a relationship between lava fountains and groundwater?
There can be.
And so can you share anything about what's going on for the groundwater system in that area?
This, I guess, would have to be classified more as speculation than anything else. But I mean, we know that the groundwater table below Leilani is about 600 feet down. My kind of perception of what's going on there is that you've got massive quantities of lava moving through the system that are effectively excluding groundwater. You're not seeing the mixing that we saw in this, if you're familiar with that area, Hulaimana, massive cinder cone that was generated, and there's some video that we have online that was taken of these mountains that formed Hulaimana. And the geologists at the time, Gordon McDonald and others that were working on that eruption, had attributed the high fountaining to a mixing of water, of groundwater with the lava as it was coming out. But I think, from all appearances anyway, the current vent, it's dominated by sulfur dioxide. Where there's not a lot of groundwater interacting at that location.
Okay,
Okay.
With that, it's 8:30, we'll let Don go as long as you want, but just want to thank everybody for coming, and especially thank Don for standing up here for an hour and a half.